From Chapter 3, what we would do in practice. So this is the picture on the right side of the screen. We had our original sample from which we could simulate thousands of Bootstrap samples, ultimately to get an estimate of the standard error, at least if we were going to construct a 95% confidence interval using that formula toward the bottom of the screen. Here it is with a specific example, where the entire point of generating that Bootstrap distribution is to get that 0.017 that's in the upper right corner, because that's our estimate of the standard error. Then we can substitute in for the standard error in that formula, and we can actually get a confidence interval. We are going to cover confidence intervals again in Chapter 6. The main difference is there's a different way of estimating the standard error. But all the conceptual stuff is going to be identical, and the same thing for hypothesis testing. We're going to cover that again in Chapter 6 as well, but the main difference is really just a different way of computing the p-value, but all the conceptual framework is going to remain the same. If you view Chapter 6 as a brand new thing, I think that's going to create a lot of extra work. It's really just the stuff that we did in Chapters 3 and 4, just with some computational differences. This is the linchpin of everything in Chapter 6 that we're going to do, the central limit theorem. The idea that as the sample size increases, the sampling distribution gets closer and closer to a normal distribution. If you want to view that using the limit definition from Calc 1, as n approaches infinity, the limit of the sampling distribution is equal to a normal distribution. That concept does make sense here. That is why the word limit is in central limit theorem, although I don't think you need that calculus stuff in order to understand what's going on here. The biggest consequence of the central limit theorem is that if you have a large enough sample size, the sampling distribution will be approximately normal. These four pictures are supposed to illustrate that idea. If you look at the picture in the upper left, that does not look normal at all. It's heavily skewed, it's heavily right skewed, but then again the sample size is only 8. If you move over to the one that's in the upper right, that looks better. It's still right skewed, but it looks better than the one in the upper left, but then again the sample size is bigger. The third one in the lower left, that one looks pretty decent. It at least looks symmetric, even though it doesn't quite look like a bell shape. And then the one in the lower right looks pretty good. If you were going to fit a best fit curve to that thing, it looks like a bell shape would just about do it. So it looks like a sample size of 100 is large enough, 40 is close, and 20 and 8 are just too small. So a natural question would be, what does large enough mean? Well, there isn't a fixed value for that, at least not with a proportion. For a single proportion, the sample size is large enough to apply the central limit theorem and say that the sampling distribution is approximately normal when the number of successes and the number of failures are both at least 10. Symbolically, that would mean that n times p and n times 1 minus p both need to be at least 10. When the sample size is large enough, the sampling distribution of p hat can be approximated by a normal distribution with a mean of p and a standard deviation of the square root of p times 1 minus p over n. At this point, that root that you use to compute the standard deviation probably looks like it just comes out of thin air. It doesn't. It's derived from a binomial probability distribution, which isn't a thing that we cover in the course anymore. It doesn't really come out of nowhere, but I could see where it might look that way. However, for right now, the important thing is just that we have it, because if we didn't have that, we wouldn't be able to compute a confidence interval. So for right now, we just need that to be there so we have something that we can use algebraically. In this example, we want to make sure we have a large enough sample size to apply the central limit theorem. Since p is unknown, we're going to have to use p hat as a point estimate. This is typically what happens for confidence intervals because you're not going to have p if you're trying to estimate it, and you do need a point estimate to be able to simplify those little formulas, the n times p and the n times 1 minus p. And that's the logical point estimate, is to use p hat, the sample proportion. So n times p hat works out to be 454. You can do the algebra if you want. It would be 873 times 454 divided by 873, and you get 454. Another way to think about it in this case is that the success is not necessarily the good thing where the failure is the bad thing. In general, a success is the outcome that you're interested in, and a failure is everything else. So here the outcome that we're interested in is somebody preferring to elect the president via popular vote. 454 people in the sample said that. And then everything else would be 873 minus 454, which is 419. So you could do it that way. If you wanted to do it as 873 times, and then in parentheses, 1 minus 454 divided by 873, that would also work. You'd still end up with the 419. If the sample size is large enough to apply the central limit theorem, here's how you can compute a confidence interval. The reason that there are two formulas there is that the one on the left is not exactly usable, because if we don't know what p is, what are we going to substitute in under the radical? And that's where the formula on the right comes in. The formula on the right is using p hat as a point estimate for p, because if we have to substitute in a number there, our best guess is the sample proportion. We wouldn't expect that to match exactly, but it should at least be close. The other part of the formula that's worth explaining is the z star. That's something called a critical value. For proportions, the critical value comes from a standard normal distribution. That's why the z notation is being used, just like in Chapter 5. The way that you can compute the critical value, or the z star, is as the bound, really the positive bound, although you could use the negative bound if you wanted to, of the central region under a standard normal curve with an area equal to the confidence level. So what that means is that if you wanted the critical value for a 95% confidence interval, you'd have a standard normal distribution with an area of 0.95 in the center, and then you would want the bound or the cutoff for that. Probably the positive one. The negative one would work fine, but the algebra feels a little bit simpler with the positive value. Here's the Bootstrap distribution and a normal approximation for that Marist pole from section 3.3. If you look at those two pictures, they look pretty similar. The one on the right just looks like a smooth version of the one on the left. That's entirely the point. That's really what's going on there. What's on the right is a theoretical version of what's on the left. So what you're going to get should be pretty similar either way, whichever one you use. Here's the critical value for 95% confidence. All I did here was go to stat key. Under theoretical distributions, I picked normal, use the default of a standard normal distribution with a mean of 0 and a standard deviation of 1, and then two-tail in the upper left, and then specified 0.95 in the center. So the typical critical value here is 1.96. Like I said before, you could use negative 1.96 if you wanted to. There's nothing wrong with that. But the algebra is a little easier if you use the positive version. Here are the common z star values. We've already established that for 95% confidence, it's 1.96. For 90% confidence, so if you do the same procedure except that you put a 0.9 in the middle instead of 0.95, you'll get 1.645. And then for 99% confidence, you'll get 2.576. On the homework, make sure you use 2.576, not 2.575. For this example, we'll make sure we have a large enough n to apply the central limit theorem, and then we'll compute the confidence interval. 265 out of 500 women between the ages of 18 and 24 said yes, that they do take a daily vitamin supplement. So to verify that we have a large enough sample to apply the central limit theorem, we have 265 successes, but if there are 500 women total, then we must have 235 failures, where in this case, a success is a yes answer, and a failure, I suppose, would be either no or I don't know. The first thing that we're going to need if we're going to construct a confidence interval is the point estimate, which would be 265 divided by 500, which is 0.53. I guess you could technically use the point estimate to check to make sure you have a large enough n to apply the central limit theorem. It would be 500 times 0.53 and 500 times 0.47. You'll get 265 and 235 like on the previous slide. If we're going to construct a 95% confidence interval for P, the population proportion, so the proportion of all 18 to 24-year-old women who take a daily vitamin supplement, the only other thing that we need is the critical value, because we already know what the sample size is, we already know what the sample proportion is, and the critical value is dictated by the confidence level. Since it's 95% confidence, the critical value, z star, is 1.96. And now we're going to compute the endpoints. So we start off with the formula, p hat plus or minus z star times that root. Then we can substitute everything in and then simplify it. And when you're simplifying, I would try to avoid rounding off intermediate steps if you can. And if you're going to go one by one with the operations, following the order of operations, you'd have to do everything under the radical first. So you'd multiply 0.53 and 0.47, then divide by 500, then take the square root of whatever that is, then multiply by 1.96, and the plus minus is the very last step. The only thing that I rounded off was I did round off the margin of error, which is everything after the plus or minus. And then I got the endpoints of 0.486 and 0.574. If you have a TI calculator, especially one in the 80s range, the thing that you want is the ANS function. It's the secondary function of the sign key. Sign as in plus minus, not sign as in trig. It looks like a minus sign with parentheses around it. It's down in the lower right corner. It's a secondary function, so you would need the second key in the upper left and then that. And what the ANS function does is it recalls the answer on the previous line. So if you multiplied 0.53 and 0.47, then divided by 500 and then enter, then you could use the square root function and then ANS, and it'll take the square root of the previous line. That way you're getting that square root without rounding any intermediate steps off. I would suggest doing that. It's the best way of handling this generally, and especially for the homework, I think that's a good idea. Then the part at the bottom here, is it reasonable to conclude that the majority of 18 to 24-year-old women take a vitamin supplement at this confidence level? No, because in order to say that, you need the whole interval to be above 0.5, and that's not what's going on here. So since part of the confidence interval is below 0.5, that's not going to be reasonable. That last part works just like it did in Chapter 3, but then again, all the conceptual parts of a confidence interval are exactly the same. It's just the way that you compute the standard error is different now. We have that root to do it instead of using the Bootstrap distribution to get it. Suppose we're given a target bound on the margin of error, so that we don't want the margin of error to be bigger than 0.04 or 0.02 or something like that. Solving for n, we get that formula, which we'll be able to use, except for the fact that if you don't know what n is, then you haven't taken a sample, so how would you possibly have a p hat? Really, we're going to have to use that formula, where p tilde just means some substitute value that we're going to have to use. There are different conditions where we might do different things. These are those conditions. If you have no idea of what p might be, set p tilde equal to 0.5. Because that'll max out the p tilde times 1 minus p tilde part of the formula, and it'll be impossible to end up with a sample size that's too small. You might get one that's larger than necessary, but that's okay. If you get one that's larger than necessary, your margin of error will be below that specified bound, so that's not a problem. The other method, if you do have some knowledge of an approximate value of p, then set p tilde equal to that. So if there was a previous study that was identical but maybe done a year ago or 2 years ago, and you have the sample proportion there and you don't think it's changed too much, you could say, well, it should be close to this number, and then that's the number that you can substitute in. The last thing, always round up no matter what, because the sample size needs to be an integer, and if you round down, you would end up with a margin of error that's slightly too big. Sometimes this is going to feel awkward, like if there's a 1 right after the decimal point. Let's say if you ended up with a desired sample size of 124.13, you've got to round that up to 125. And that feels weird because usually that's not the way that you round. But for this, it's always round up to the next integer, not round to the nearest integer, which is the way that most people normally do it. To compute a desired sample size, you need 3 things. You need the bound on the margin of error, which that has to be specified somewhere. You need the critical value, which is dictated by the confidence level. So if you had the confidence level, that would be enough to get one. And then you need to know what to substitute in for p tilde. Either we have a reference value that we can use, and we're going to use that, or we don't, and then we have to use 0.5. Here, if you look at that third bullet point, the within 4%, there's the bound on the margin of error. Converting that to proportion form, it's 0.04. 90% confidence is enough to give us the critical value. If that's our confidence level, then z star is 1.645. The other thing is the p tilde, which is in the second bullet point. We do have a reference that we can use. It's believed that about 70% of cardholders carry a non-zero balance at the end of the month. There's our p tilde. Substituting into the formula and then simplifying, what we end up with here is 355.17, at least rounded to 2 places. But then we've got to round up. This is one of those scenarios where the rounding feels a little unusual, where this isn't typically the way that you do it, but for sample size calculation, you got to round up no matter what. If that was rounded down to 355, that would be wrong, because if you did that, you'd end up with a margin of error that was a very little bit too big. Here's another desired sample size example where we're looking for the same stuff: the bound on the margin of error, a confidence level so we can get the Z star, and then a P tilde if there's a reference that we can use. Margin of error of 6%, that's fairly explicit. The bound on the margin of error is going to be 0.06 written in proportion form. 99% confidence, that tells us that Z star has to be 2.576. And then if you look through the wording, there's no reference that we can use for P tilde. And this is where you need the 0.5, where you just have nothing to work with. And looking at the subject matter, the percentage of businesses that plan to hire additional employees in the next 60 days, that's one where to try to get a point estimate with nothing to work with, that's not really a plausible thing that you can do. So this is one where we just have to say, okay, we don't have anything to work with here. We got to set P tilde equal to 0.5. Substituting in and simplifying, we get 460.8, which needs to get rounded up to the next integer, which is 461. At least this time we had an 8 after the decimal point, so the rounding feels sort of conventional. There's how you would find a p-value in a general sense, using an approximation of the sampling distribution of p hat under the assumption that the null hypothesis is true. That's what we did in section 4.2, where we're finding p-values using a randomization distribution. That is an approximation of the sampling distribution. There's just a different approximation that you use in Chapter 6. But with this Punxsutawney Phil example, we can go through how we did it in Chapter 4, and then we'll go through how it would work if we did it the Chapter 6 way instead. This is what we had in Chapter 4. We had a null that p was equal to 0.5, and then a left tail bounded by 0.392, which is 47 divided by 120. That's going to be our p-value, 0.011. The Chapter 6 way of computing a p-value is that if the sample size is large enough to apply the central limit theorem, and we make the assumption that the null hypothesis is true, the sampling distribution of p hat can be approximated by a normal distribution with a mean of p0 and a standard deviation of that root, where p0 is just the value that's in the null hypothesis, the numerical value that's there. And that's also what you would use to check to make sure the sample size is large enough. This is kind of a subtle point, but it's worth bringing up now. For a confidence interval, when you're checking to see if the sample size is large enough, there you would use p hat because you don't really have a value that you can substitute in for p other than that. But with the hypothesis test, since you do all the computations assuming the null hypothesis is true, you use that value in the check to make sure that you have a large enough sample size to apply the central limit theorem. That's why if you look at the bottom of the screen, there are p0s instead of p hats. For the Punxsutawney Phil example, p0 is 0.5, since the null hypothesis is p equals 0.5. N times p0 and n times 1 minus p0 are both 60, which is greater than or equal to 10. So we're all set for the central limit theorem. So we can approximate the sampling distribution using a normal distribution with a mean of 0.5, coming directly out of the null hypothesis, and a standard deviation of the square root of 0.5 times 0.5 divided by 120. If you round to 4 places, it's 0.0456. We can have the same sort of comparison that we had before. Side by side, on the left we have the randomization distribution from Chapter 4, and on the right we have the normal approximation from Chapter 6. And just like what happened with the confidence interval, if you look at those pictures, you think the one on the right looks like a smoothed out version of the one on the left. And again, that's exactly the point. The one on the right is a theoretical version of what's on the left, which is why it has a nice perfect shape. And it looks like you'd get similar p-values. And that's exactly what happens. There's the p-value that you'll get using the normal distribution with a mean of 0.5 and a standard deviation of 0.046. StatKey only takes the standard deviation to 3 places, so I couldn't type it in as 0.0456. Then the cutoff is still going to be the same. It's still going to be 0.392. And we end up with a p-value of 0.0094, which is pretty close to 0.011. Not identical, but those are pretty close to each other. There is another way to compute the p-value using a normal distribution, and that's to use the test statistic. You don't need it for a proportion. obviously, we've already computed a p-value and we didn't use the test statistic. But you can do it with a test statistic, and that's the way that you have to do it for means. So it might be worth getting used to doing it this way. The test statistic, which our book denotes with a Z as opposed to Z star, I don't know if I'm that big of a fan of that notation because it's really easy to get those things confused. I personally always just write out TS for test statistic and don't worry about writing it as a Z. But what you get for the test statistic is what you get if you standardize p hat using the mean and standard deviation that we have, or that normal approximation. So p hat's 47 divided by 120 minus the 0.5 for p0 that's in the null hypothesis, then divided by that root that's our standard deviation, and you end up with negative 2.373 if you don't round any intermediate steps off. Look at what happens if you do round off. You get something a little bit different. You get negative 2.368. That by itself is not the end of the world. However, as far as the homework is concerned, you're generally better off not rounding off any intermediate steps. Because what might happen, and this does tend to happen every once in a while, if you round off intermediate steps and you get a slightly different test statistic, the homework will count that as correct, but it'll count the p-value as wrong, even if you do the p-value correctly in relation to that test statistic that you have. The reason for that is that the test statistic and the p-value answers would both have a tolerance, and it's very possible to end up within the tolerance on the test statistic and then outside of the tolerance with the p-value. So to avoid that, I would say for a test statistic, don't round any intermediate steps off, and then you'll be fine. If you're going to use the test statistic to compute a p-value, you need to use a standard normal distribution. Because if you're going to do that transformation to get the test statistic, so to subtract the mean and divide by the standard deviation, you have to do that to the entire distribution. So effectively here you'd be transforming a normal distribution with a mean of 0.5 and a standard deviation of 0.0456 to a standard normal. It's still going to be a left tail, and now the test statistic would be the cutoff instead of p hat. I do get a slightly different p-value here. I'm getting 0.0088 instead of 0.0094. The reason for that is because in the other one with the 0.0094, I had to round the standard deviation off. It's a slight difference, but that's why I'm not getting the same number. The note at the bottom I already said, but I think it's worth repeating. For a single proportion, you can compute the p-value using the test statistic or without the test statistic. There are two different ways of doing it. That won't exist with a single mean. With a single mean, you have to use the test statistic. In this example, a computer chip manufacturer claims that no more than 3% of the chips it produces are defective. We have a sample of chips where we're looking for evidence against that claim. And evidence against that claim would be if the proportion of defective chips is too high, if it's higher than 0.03. So that's why our alternative hypothesis looks like that. Our sample proportion is 19 divided by 400, which is 0.0475. The first thing, if we're going to do a hypothesis test, is to check and make sure we have a big enough n to apply the central limit theorem. N times p0 barely gets there, but it gets there. 12 is greater than or equal to 10, so that is large enough. The number of failures, n times 1 minus p0, that's huge. So that's not a problem at all. 388 is much bigger than 10. We have a large enough n, so we can apply the central limit theorem, and that means that the sampling distribution of p hat can be approximated using a normal distribution with a mean of p0, which in this case is 0.03, and a standard deviation of the square root of 0.03 times 0.97 over 400, which to 4 places would be 0.0085. Finding the p-value, here it is with a normal distribution with a mean of 0.03 and a standard deviation of 0.0085. Then the cutoff is just going to be p hat. Stat key only accepts the p hat to 3 places, not 4, which is why I have it as 0.048 instead of 0.0475. But it's going to be a right tail because of the greater than the alternative hypothesis, and we get 0.02, which is less than 0.05, so we're going to reject the null. The other way of computing the p-value would be to use the test statistic. There's a test statistic computed without rounding off any intermediate steps. I took the p hat 0.0475 and standardized it, and I got 2.0517. And since I'm using the test statistic as the cutoff, I need to be using the standard normal distribution as a reference. So if you look toward the right side of the screen, I've got a mean of 0 and a standard deviation of 1. Still a right tail, but now the cutoff is the test statistic. Again, stat key only accepts it to 3 places, which is why it's 2.052. And then what you get for the p-value is the same. It's 0.020. In this example, it doesn't look like there's much of a change from what happened in the 2015-16 flu season to what happened in that sample the next year. So what we can anticipate is we should have a monstrous p-value. We're looking for evidence of a change, like it says in that third bullet point. So change, no specified direction. We need a two-sided alternative. We need the not equal to in the alternative hypothesis. The first thing to check is to make sure we have a large enough sample to apply the central limit theorem. That's not going to be a problem. 749 times 0.42 and 749 times 0.58 are both substantially larger than 10. Since we have a large enough sample size to apply the central limit theorem, we can approximate the sampling distribution of p hat with a normal distribution that has a mean of 0.42 and a standard deviation of the square root of 0.42 times 0.58 over 749, which is 0.018 to 4 places. And here's the p-value. It is a gigantic p-value, like we would have anticipated. This is done using a normal distribution with a mean of 0.42 and a standard deviation of 0.018, where then you can just use p hat as the cutoff. It's a two-sided alternative, so I have 2 tails selected in the upper left, and then the only thing I had to specify was the 0.41 because that was our p hat. So we're getting a p-value of 0.578 because really it's what you get when you double that left tail of 0.289, or effectively what you get when you add the left tail and the right tail together. That's going to be the same answer. 0.578 is much bigger than the significance level of 0.05, so we're not going to reject the null hypothesis here. If you would rather compute the p-value using the test statistic, you can. Up toward the top is the test statistic computation, taking the p hat of 0.41 and standardizing it. And then if you're going to use the test statistic as the cutoff, the reference distribution needs to be a standard normal, which you can see, mean of 0, standard deviation of 1 toward the right. Again, it's a 2-tail, and now my cutoff is going to be the test statistic, so negative 0.555 instead of negative 0.5545, because again, stat key only accepts this to 3 places when you type it in. And then you get the same p-value, 0.578.